Okay, good. Welcome again to the Machine Learning Coffee. Today we have a guest from far, from Tampere, University of Tampere, Jaakko Peltonen, whose title is here. Welcome, Jaakko.
Tampere is not that far. Tampere is very close. Just 2 hours by train, a little more by bus. Come visit. It's very easy. Good morning. Yes, I'm Jaakko Peltonen. I'm a professor of statistics and data analysis at Tampere University. So one of the responsible professors for our master's program on computational big data analytics. And today, I'd like to talk to you a little bit about a few recent things we've done with large hierarchical text data, especially online discussion venues. So on the slides here, you can see a few of my fellow researchers. Ishbul is a postdoc. Zivan is a soon to graduate doctoral student. Jyrki and Carl are fellow professors. I also, in addition to being at Tampere, I have a visiting professor status here at Aalto. So let's get right to it. I'm going to be basically talking about the contents of these 3 recent papers, and I basically just collated the slides from them, so I have far too many than are needed for this coffee seminar, so I'll be skipping the less interesting ones. Let's first talk about why I need to be here, why I need to talk about this. Thing is, discussion venues are very important because online discussion practically occurs very often in them. And many of those venues have an organization, a hierarchical organization. For example, Suomi24 is an example of a Finnish conversation venue which is organized as a hierarchy. Another example is product reviews in a place like Amazon, where the products themselves have a hierarchy, and then reviews, of course, are available inside that hierarchy. And those hierarchies are created by administrators, but administrators are not really experts in content. They make their best guesses about what kinds of sections, categories, links between them are needed, but in reality they are not really able to fully describe the true variety of content, and it may not even be possible to fully describe it only as a hierarchy. So there is typically a mismatch between what the hierarchy is and what the content is, to some degree. So then, if one is interested in what the actual range of interests of people are when they have discussion in these hierarchical venues, it would be important to extract those interests in a data-driven way, as well as the relationship between the possible interests to authors and to the places where the discussion happens, the sections of the hierarchy. For example, consider Suomi24. It's one of Finland's most popular message forums. It's a very long-standing message forum. It's been around since the beginning of 2001 around. So there are now around 18 years of conversation data in that forum. There are over 2,000 sections where conversation can happen, organized as a hierarchy. We'll come to that later. There are millions of threads and even more usernames. 5 million threads, about 60 million usernames, which is kind of interesting considering that there are much less people in Finland than that. So you can make your own inferences about that, what that actually means. Mostly it's in Finnish, but there are also a number of Swedish language sections. So you can see a few of the sections listed here. The section related to various feelings here, things related to marriage and marriage proposals on here, things related to pets and pet-related hobbies. And in addition to having a lot of data, it's also visited a lot. In 2015, this is an old number, but still in 2015 there were nearly 1 million unique visitors each week. So it's really a popular place. So message boards, organized sections and subsections and so on are an example of this kind of hierarchical venue. There are others like Amazon. And I should mention that there are also some places where discussion occurs which may have a flat organization, which basically have just like a root and then a large number of sections under a root. Reddit is an example of that. You basically have the Reddit front page and then you have subreddits under that, but you don't have subreddits and subreddits and so on. But there are these venues, in particular message board, which may have an extensive multi-level hierarchy, which then have typically a tree of sections. And this poses a problem because this administrative created division, which I already mentioned, doesn't really suffice to describe the variety of the semantic content. So a common user may not really need to know. If they have a bunch of favorite sections, they simply might want to go to them and discuss there. In some cases, they might benefit from results of data analysis, but at least administrators and analysts would benefit from it, because obviously these kinds of message forums are a treasure trove for analyzing how people behave, what their interests are for various purposes, for analyzing political interests, for analyzing consumer interest, and all this kind of thing. So analysts like to know, but also administrators may like to know about the underlying variety of content, because if the hierarchy turns out not to support the content, they might want to edit the hierarchy, add some new sections, add some you might like to also see type links, and that way increase their user engagement, keep people staying there on the message boards, keep them seeing ads, keep them generating money for the company running the board. So there are a number of ways in which the interests may differ from the available hierarchy. You may have threads that are available in very different sections, but they may talk about practically a very similar type of content. But on the other hand, a single leaf section of the hierarchy may itself talk about multiple types of content, so it's not a one-to-one match between content and hierarchy. Of course, conversation threads are themselves a compilation of posts from multiple users, which each have their varying interests. So a thread may start out from a post by one user about a particular thing, but it may then diverge and over time flow towards different interests and back again. And it's also not a correct assumption to think that users choose the correct section or the best section where to talk. They may not be aware of all the over 2,000 sections where they could talk about these things, so they just choose based on whatever they do happen to know. Also, there may be situations where user just doesn't have any good place where to talk about something. Some topic just may not have a dedicated section or a sufficiently close by section, so they end up being discussed just wherever users feel is good enough. And this may then happen in several places. So there are many ways in which the administrator-created hierarchy may not match the content. But in general, in order to analyze what the content is, we would need to somehow make very simplistic representations for computational purposes. So this is an example of a thread about the type of clothing, farkkuhaalarit, type of overalls, and these are some of the popular words in there as a word cloud. So this makes it easier to analyze at a glance what seems to be the topic in this particular thread rather than reading through this whole mass of text. Problem is, this is just one thread. What happens when we go to multiple threads? It still becomes a little bit too overwhelming to see what is available. Millions of threads, remember, so looking through millions of these is not feasible either, so we still need to be able to simplify. This is where the computational analysis comes in. So I'm going to be talking first about a couple of topic model based ideas. So what's a topic model? Many of you may be familiar with it, but others may not, so I'm going to try to present it first as a very simple description. So think about bowls of candy. If you were to describe them to somebody who wants to choose a bowl, you wouldn't describe every single item of candy there. Instead, maybe you would say that, okay, I've had a bunch of candy bags I bought from a shop, and you might say that, okay, this bowl is half Assamix and half Tutti Frutti. This is 2 parts of different Tutti Fruttis and 1 part remixed. So that's a sufficient description for most people. You don't need to describe each individual candy. Now, what if you saw the bowls, but you didn't know what the mixtures were? But you do know what the original candy bags were. Could you determine what the mixtures were? Maybe you could if you were familiar enough with the bags of candy, with the different types of candy being sold. What if you also didn't know the bags of candy? Could you find out what the original bags were, assuming that there were only a few different types of bags from which these bowls were mixed? Well, of course, we're not really talking about bags of candy. The bowls are really the documents containing a mix of words, and the original bags of candy are the topics. So we are trying to find out what the original topics may have been from the observed mixtures of words available across a bunch of documents. So topic models represent these documents as very simplistic bags of words. They don't have to be individual words. They may be engrams, or they may be keywords or key phrases, whatever are things that you can count out of the documents. You can use topic models to represent them. And it's a two-step process. Topic models assume that documents are generated so that you first choose what to talk about the topic, and then you choose what to say, a word from that topic. And these two distributions, what are things that you can talk about, and what are words available in each topic, these are fitted to a set of available data. There are a number of topic models already available. Latent Dirichlet allocation is the most common one. There is a non-parametric version called the Hierarchical Dirichlet Process. So, roughly speaking, the mathematics really, well, actually the description that I already said looks like this. You repeat for each document, that each document gets a mix of topics. Then for every word in a document, every word comes from some topic, and every topic has a mix of its own words, and the word is chosen from the words of that topic. Mathematically, there's an equation that looks a little bit like this. It's a simple mixture of probability distributions. Problem is, when we have these hierarchies available, this here is a picture of the Suomi24 hierarchy, and this is a picture of a small part of the Amazon.com product hierarchy. How do we adapt topic models for situations like this? It's a challenge to take the known section structure into account, and when you further know authors, like usernames, Suomi24, how do you take them into account? You might think that you can just first run topic models without taking hierarchies into account, and then just later summarize per section, summarize per branch of the hierarchy. But that really is kind of a naive approach. It ignores, during the learning of those topics, it ignores the predefined organization. So it would be better to take the hierarchy into account while you learn these probabilistic models. Hierarchical Dirichlet processes, you might think that, okay, the name sounds nice, hierarchical. Maybe that is a solution. No, actually it turns out that hierarchical Dirichlet process can't readily be extended into a situation where you have really a deep tree and where documents could arise at any node of the tree. Like consider the Amazon case. Here you have documents under ice spearing equipment, but you can also have documents under a parent section like ice fishing accessories here, or documents under phishing accessories here. So documents can arise at any point in the tree. Basic hierarchical Dirichlet processes are more suitable for places like Reddit, where you have a flat structure, but when you have a deep structure, you need something more. So I'm going to be talking about that. So a couple of models where you can use an extension. The first is called THDP, Tree Structured Hierarchical Dirichlet Processes. Turns out that name is not quite as unique as we hoped. There are other people who have used this tree structure name, but I'm talking specifically about the model that we introduced. So it's a non-parametrical version of a topic model, a hierarchical topic model that does take this kind of deep hierarchy into account and allows text to come from any place in that hierarchy, and works well, outperforms more basic models. So if this is a graphical representation of a hierarchical Dirichlet process, if you're unfamiliar with plate model representations, this may not tell much to you, but what it is supposed to say is that there is an overall distribution called G0 there, which comes from a prior, but that overall representation, overall distribution represents what is the overall range of possible conversation topics in the data set overall. And then each individual document under that would then be a child of that distribution with a few changes. And then the words in each individual document are generated from that child distribution. So this is really a flat representation. You have an overall parent, and then you have everything under that parent. Here is what we want to do. This is a representation where you have a document arising out of some parent. That parent has a grandparent, the great-grandparent, and so on and so on and so on until the root of the hierarchy. Here's an instantiation of that idea for a particular example hierarchy, which probably makes it a little bit more clear. So you have a root, which represents the root of the actual, let's say, product hierarchy in Amazon or conversation hierarchy in Zone 24. And the root may have children, the children may have grandchildren, so on and so on. And at any point, any one of these distributions may actually generate documents that then further contain words. This is the rough idea. And another reason why I chose these particular papers to present here is that they all have a kind of a food theme. Why do they have a food theme? Well, it turns out that these probabilistic models, non-parametric probabilistic models, topic model types are often described with food metaphors when you talk about how they are fitted to data. In the case of in the case of Dirichlet processes, this metaphor is called a Chinese restaurant process. The idea is that when you are generating a document, each word has to choose what topic it shall come from. And that choice is depicted in the same way as a customer coming into a Chinese restaurant. They see a number of people sitting around tables that each serve dishes, types of foods. The types of foods are going to be the topics. And the customer needs to choose where to go, which topic to pick, which thing to talk about. So they choose based on which tables seem to be popular. They choose some of the tables that have the most previous customers, but they also have the possibility of going to a new table. This analogy is why this is called a Chinese restaurant process. When you have a hierarchical Dirichlet process, which remember had the parent and then a flat organization under it, that is called a Chinese restaurant franchise. So it is assumed that the restaurants themselves come from a parent franchise, so that the tables don't get their dishes directly, they get them from an upper level parent franchise, from tables in the parent. Well, when we have a deep tree, we also name this something. We called it an imperial Chinese banquet, because the idea is that you have like a palace which has multiple levels, and it has places where you can get food at multiple levels. So think of the words again as customers coming and the documents as a restaurant. Customers sit at tables, but the tables are given food by waiters. The waiters fetch their food from some delivery station, but the delivery station has a number of tables, and those tables get their foods by waiters from an upper level delivery station further up in the palace, and so on until somewhere top side in the palace you have finally the kitchen where the foods are actually being prepared. So we have the same kind of analogy here, but now it just extends deeper in the tree. As a result, we get a sampling method. The details I will skip due to lack of time. So typically these kinds of models are evaluated by a number of methods. One of these methods is how well they can predict document content. Are they surprised by the content of new documents that they hadn't seen during the fitting of the models? That is measured by perplexity. And another thing that you can do in our case, since we have a hierarchy, is that you can try to predict where in the hierarchy did the document come from. If you see the content, can you predict which part of the section hierarchy it was from? So we try these two different types of evaluations on a number of data sets whose characteristics are mentioned there. They are basically subparts of the tree, just so that we have separate evaluations. I think I will skip this, but suffice to say that you can analyze topic models by the distributions of words in each topic. Do they seem to make sense? This is an example for Amazon products under fishing equipment. And if you look at this long enough, you will see that they actually do make sense. They have things like scales, weighing things, how accurate the scales are, and you measure them, and so on. So each topic has a very meaningful sense of how they talk about an individual semantic type of content. And we have also listed where in the hierarchy, in the product hierarchy, they were used. So this was about that. This is the product hierarchy that I was just talking about. And it is also something where we can demonstrate that the topics do get shared across the hierarchy in an intelligent fashion. So topics that are in a parent section, they can be shared differently to different children of that parent section. So this is an example how some topics from the parent section, ice fishing accessories, end up with different proportions in a child section, the ice spearing equipment example. So then the numerical evaluations that I mentioned, predicting content of new documents, how surprised you are by them. So perplexity is how much you are surprised. So smaller numbers are better. These gray numbers representing our model work better than a comparable HTTP model, which is trained separately across sections of the hierarchy. Then the other case, predicting where a document comes from if you see the content. Here it's accuracy, or well, actually it's F measure in an information retrieval sense. You take the K best predictions, then you check across them that okay, are you able to retrieve the correct section among the first few. So in terms of F measure, higher numbers are better, and again our model performs better than a traditional HTTP style model. Some other details. Concluding this part, we propose this hierarchical variant of Dirichlet process with a deep tree-based hierarchy. It can take these kinds of hierarchies into account, and therefore it models contents of texts better than a traditional model. Then, another thing whose most details I will skip because this can be seen as an extension of the previous one. What if you also have the authors? You want to take them into account, the authorship of the texts. What's the difference to the previous model? Well, again, here was the hierarchical Dirichlet process. Here is the author tree-structured hierarchical Dirichlet process. What's the difference? Well, here at the bottommost level, the topics generate not just words, but also authorship of the words, who wrote each word. So this is a factorized distribution. Now a topic has a distribution over words and a distribution over authors, and each word is paired with the author indicator of who wrote it. Again, you can instantiate the same thing across an example hierarchy. So now at each section, at each point of the tree, you can get documents which have words, and those words in turn have the actual word, and then the author who wrote the word. I think I skipped this generative part and instead just say that again we have a food metaphor for the inference. Now we call this the fine chocolates banquet, because we wanted to have something where you can imagine that you have as the objects, as the customers, things that have both the type of food and an author. So we imagine that, okay, maybe you have some chocolates that are so fine that the maker of the chocolate signs them. So it's very similar as before, but now when the customers arrive, the tables contain a pair of a distribution of food types and a distribution of author types in this factorized fashion that we had in the plate model. And otherwise, the idea is the same. You have a large palace, and then the tables have waiters which fetch the distributions from upper level tables and further up and so on until the topmost level kitchen. Again, we get a Gibbs sampling algorithm for this, whose details I skip. Now, we tried this again on a number of data sets, slightly different from the previous ones, but again, similar statistics. And you can again try to predict a few things. Remember, now you have the document content, you have the sections, and you have the authors. So, skipping the details, one thing is you can try to again be surprised by, you can measure how well you are surprised by new documents. Given the knowledge of where the document occurred and who wrote it. So basically the question is, can you believe what this person just wrote here? Smaller numbers are better, less surprised better, and we perform better than HTP type models that are trained either based on the author or based on the combination of the author and the section. So we are able to take this hierarchy and authorship into account better than the naive models. Similar results arise in all the datasets, so our model works pretty well. The other example is predict the author given the content and the section. Basically, who could have written this thing here? Now, you can measure this by, in this case, it's classification accuracy. Larger numbers are better, and again, we do a lot better than these traditional models, or adaptations of the traditional models. So this was a model that you can see as an evolution of the previous example, and in addition to hierarchy, it takes authorship into account. A little bit over time, but lastly, I wanted to come to the meat of this presentation. Not really, but it's a nice accidental analogy. So this last part is called PV, online forum posting analysis with interactive hierarchical visualization. I didn't come up with this acronym. It was suggested by my student. So PV is also, in addition to being this acronym, it is also the Finnish word for steak or meat. So here is the meat of the presentation. So we just built some probabilistic models, right, for these documents, but those still give you just numerical summaries. What if you really wanted to explore? So we introduced a system for exploration of these hierarchical venues, where we were especially interested in how the content, how the variety of content differs from the organization in the hierarchy. It is based on scatterplot-based visualization created by dimensional reduction, coupled with a coloring that is also created by dimensional reduction to show the hierarchy. Remember, we have thousands of sections, so even the hierarchy is not that easy to show. So we needed a way to connect it to the variety of content. So most visual analytics tools do not try to do this. they focus on things like temporal changes in document trends and so on, or networks of how people converse. So we are not interested in that. We are interested in comparing the hierarchy and the content. We want to illustrate that theme in a compact fashion. So to answer the questions that what kind of topics are people discussing and where is the discussion happening, we wanted to allow efficient browsing to find that, okay, which discussion trends are the individual threads or interests related to. We wanted to show the relationship between the conversation threads, both in terms of the content and the position in the hierarchy. So, for example, given a thread of interest, what other similar threads exist? We want to answer this question as well. And all these, even when the amount of content grows and grows and grows. This is what it looks like. There's a set of 5 linked views. There is a zoomable content-based map, and then there are linked views to that. First 3 views are always there, and the latter are on demand. So the content-based map is a scatter plot created by dimensional reduction. Threads are organized by content, so that the clouds you see here represent threads of similar content. Similar threads are shown nearby. You can zoom into this map, we'll see that later. The colors represent the sections of Zone 24 and their similarity. Similar colors are coming from similar places in this section hierarchy. I mentioned the zooming, I will skip the detail. There is another detail related to how the zooming works, how you can do it in an efficient and interactive fashion. I skip that. There's a thumbnail view, so you can use that to browse while zoomed in. There is the thumbnail view of the hierarchy. You can use that to actually select a bunch of sections. And there are panels where you can, after you have selected an area, you can see what is the content inside there, as well as the content inside an individual thread. So this is what it looks like when you select a small amount of these sections. They get highlighted in the scatter plot, so you can easily see where semantically the content in an individual set of sections is divided in this content-based map. So you can see, for example, that this set of sections is really divided into different areas containing different types of semantic content. And you can see the list of sections also there. You can zoom in as much as you like, and then you can select individual groups of sections, such as this. You can find the names of their sections, you can find the names of the actual thread contents, you can see the selected area, and you can see the threads that are in there. In this case, it turns out to be related to hearing-related things. Problems with hearing in humans, also problems in dogs, for example. And that way you can continue to browse. And this design supports well-known taxonomies of interesting things that people need to do, tasks that they need to do during browsing. I think I will skip a lot of the details. We are using a dimensional reduction method to create a scatter plot. We are using a similar dimensional reduction method, but not the same one, to create the colors. There is a lot of detail that how do we make sure that the resulting colors and the distances are meaningful and do not show artifacts. There is also a lot of detail about how we are able to create efficient zooming so that in a huge data we can easily group dots into larger clusters, how we can basically show a manageable amount of detail. But I skip all of that. We tested this kind of browsing with people who needed to perform simple tasks, and this was using the Suomi 24 corpus, of course. So we asked people to find threads related to hearing, or find threads related to Matti Nykänen, or find threads that are in the Swedish language, or find threads related to hair care, all so that they needed to go beyond the immediate obvious solution, meaning a section dedicated to that topic, because that is something that anybody can find very easily by a simple Google search. The point is, how do you find the content that goes beyond that section? How do you find the discussion related to a topic of interest that is happening elsewhere across the hierarchy? We wanted people to find those. So we gave them a starting point, but we wanted them to find content outside that known section. We compared this to a baseline system, which is basically something which has the hierarchy available and has simple browsing tools, but doesn't have this content-based scatter plot. And we measured the results by several ways. Qualitatively, people seem to like it. They made several observations. They found interesting things, like they found that Swedish is sometimes used for trolling instead of actual real content. And they were able to notice good properties of the system, like the content related to Matti Nykänen was able to, they were able to easily find that even though it arose from different sections. So they were able to find more diverse content than in the baseline system. And they were able to do this even though, of course, this more complicated system had a slightly more steep learning curve than the baseline system did. Then we evaluated whether people were able to find relevant threads in a short amount of time. So we had a measure that balanced the amount of relevant content they found versus the time that they spent to find it. So basically, the amount of retrieved relevance in unit time was our measure, and we strongly outperformed the baseline system with a statistical significance. Also, in the questionnaire that we gave to the users, we asked a number of questions related to how they liked using different aspects of the system, whether it made them confident in their results and so on. So we had 18 questions, about half of them were statistically significant, and all of the statistically significant ones were in favor of this Pihvi system. So here are a number of those questions. People wanted to use Pihvi more frequently than they wanted to use the baseline. They found it less cumbersome, they felt more confident with it, they found it more easy to find what they were interested in, they would use it again more often than they would the baseline, and so on. So a lot of nice results in that sense. So here's the same thing numerically. So Pihvi is the yellow set of bars, and people preferred it quite strongly compared to the baseline. And overall, also all users preferred the Pihvi system. So we introduced this interactive system for visualizing and exploring this hierarchical text corpus of the forum postings. It shows this scatter plot and combines it with an optimized coloring, as well as a number of other tools for exploring and zooming and browsing. So we evaluated all of these methods in a number of numerical ways, but of course these are also tools for exploration and finding novelties, and these systems really can be used to find interesting novel things. For example, it turns out that there were some discussions that were placed close by related, for example, to sports and to animals. Why? Well, it turns out that the close by threads turned out to be related to running. And why were those placed close by? Well, it turns out that people were walking their dogs, and sometimes they were walking their dogs so much that they actually gained exercise from it. So that turned out to be related to running otherwise. And there were also some other similar examples, like let's say, there were some discussions that were split between interior decorating and, on the other hand, animals. Can you guess what that is? Well, it's aquariums, because aquariums are not just homes for your fish pets, they are also a part of the way that you decorate your home. So these are examples of simple but new to me things that we were able to easily find on this kind of browsing system. And of course, in the hands of dedicated analysts, this can yield a lot more. This concludes my coffee presentation. Thank you for your interest.